On this video, we are going to deal with a virtual laboratory activity regarding refraction of light. For our objectives for this virtual lab, we have described what happens to light when it shines on a medium. Explain light direction changes at the interface between two media and what determines the angle. And lastly, we have to apply Snell's law to a laser beam incident on the interference between media. So we are going to use a virtual simulation for this lab activity coming from PET, Colorado, which is the bending of light. Let us explore the intro screen, find out some things that happen when light rays shine into water. Let us also figure out how to test what happens when the light rays come from underwater. So as we explore the intro simulations, let us answer the following questions. Have to describe the behavior of light when it shines on the water. Provide examples for a variety of incident angles to support your description. Number 2, what changes if the light is underwater and the light goes into the air? And number 3, what changes if you shine a light on grass? So let's look into now the simulation from PET, Colorado. So we have here a laser pointer that's already on, and we have two materials with two different index of refraction. We have air, which is 1, and the index of refraction of water is 1.33. So as we move the laser pointer, we can see a refracted light and a reflected light. So we now use a wave instead of a ray. So we will go back to the ray as our point of example. So here we can customize and change. So we change the upper portion into water and change the lower portion into the air. So what we can see now is a phenomenon called the total internal reflection. So here at this point, there is now a refraction of light coming from the water and moving into the air. And there is a little amount of light that is being reflected. So the use of protractor can identify the angle that separates between the angle of incidence and the normal line and the angle of reflection or refraction between and the normal line. So as you can see here, we are looking into the angle where we are able to start the refraction. At this point, we have total internal reflection. So we will change the medium on the lower part into a glass. So you are able to notice what happened to the refracted ray of light from the normal line. So we'll change again from water to air. So I hope you have noticed what happened to the ray of light to the refracted light as we change the medium with different densities. There is changes that is happening between the angle of refraction and the angle of incidence. still we have the total internal reflection. There are changes that is happening when we have water to glass. We change again to air. So there is another changes that happen. Okay, so let's move on now to the next part of the simulation. Now, let us investigate the prism screen or the prism simulation, and we are going to use two lenses, the convex and the concave lenses. So before we move into that, as we investigate the prism simulations, let us answer the following questions. We have first one, what happens to the light as it passes the convex lens? So these are the questions that we need to take note as we move along on the simulations. Then number two, what happens to the light as it passes the concave lens? And number three, how do you describe each type of lenses? So let's go on now to the prism part or prism simulation of the bending of light simulation. So we have here still the laser pointer, and we have a convex lens. And you're going to use a laser pointer with a few number of rays so that you're able to clearly see what is happening on the light as it passes through the different lenses. So you can notice that there is a common point where the light focuses. So this is the reason why we call a convex lens as the converging lens, because it focuses the light coming from a source. So after it passes through that medium or through the lens, it focuses the light on a certain point. So you can come up with the example of this kind of lens as the magnifying lens. So wherever we place the source of light, it will still converge all light rays to a common point. So let's use now the concave lens. So here, the concave lens, we are able to scatter the light. This is the reason why we call the concave lens as the diverging lens. So it scatters the light rays from the light source as it passes through the lens itself. So whatever angle that we do on our concave lens, whether we place it on the other side, it still scatters the light rays. So if we are going to do that to the convex lens, same thing what we did to the concave lens, it still do the same thing. So it focuses the light. Now I have here a circular lens, so we can consider it as a convex lens. Still, it converges the light. So I use here now a white light. So we can notice that there is a rainbow at the far end of the screen. Okay. So if we are going to change the index of refraction, so we have here from glass, we're going to change the environment into the water. So you notice that there is now a changes in how the uh, converge converging of light that will take place. So it converges much farther from the point where we started if the environment is in the air. So as you can see, they are converging on that position. We click on the normal line. So we have here the concave lens. We have that as the normal line. So the farther you are in the source, much lesser is the scattering light. So both the object has the same medium and the environment, so there is no refraction that will take place. So I have here air now as the environment. So you can notice the convex lens converges, focuses on one point, while the concave lens scatters all the light rays that have been converged. Moving on to our next part. So we need to complete the data table as we use the more tools screen from the simulation. So I have here a constant value for the angle of incidence for all scenarios that we are going to do. We have 30 degrees for the angle of incidence. So we're going to do to light the source of light from air moving into the water. So we are going to look into the angle of refraction from the simulation, and we are going to calculate the refraction, the angle of refraction using the Snell's law. The Snell's law gives us that n sub 1 sine theta sub 1 is equal to n sub 2 sine theta sub 2. So in order for us to calculate for theta 2, so we are going to manipulate the formula given to us by the Snell's law. So the second scenario now is from water into the air. Then the third scenario is from air to into glass. Then the fourth scenario is from water into glass. And then the fifth and the last scenario is from air into a medium with an index of refraction equal to 1.22. So let us start our simulation. So we're going to click on more tools. So I have here materials with air and glass. So here we can also click on the angles. So we can identify clearly what will be the angle of incidence, the angle of refraction, and the angle of reflection, if there are angle of reflection. Okay. So at this point, we are not going to use anymore the protractor because in the more tools screen, we can identify already the given angle. So we're just going to set our pointer, our laser pointer into 30 degrees. Oops. Okay, it's 29.7. Okay, that's 30 degrees. So we have here 22 degrees. That's from air to water. The angle of refraction is 22.0 degrees. Okay, so we need to take down notes as we move along on our simulation. Okay, so we are going to change one material. So we have water as the first material and then the second material here. So we have water, water, no reflected ray and no refracted rays. So the second material will be air. So we have a 41.8 degrees of refracted angle. So still our incident angle is 30, but based on the law of reflection, the angle of reflection is still 30 degrees. So you can notice that the intensity is equal to 4.62 on the reflected ray and the refracted ray is 95.38%. So the intensity of light differs based on the amount of light rays that has been refracted or reflected. So again, our angle of refraction for this scenario is 41.8 degrees. So we change now again from air. So we have air to glass. So our angle of refraction is 19.5 degrees. So again, this is air moving to the glass. So the light coming from our light source is coming from the air moving into the glass with an angle of refraction equal to 19.5 degrees. So we're going to change again our material for the first one. So we have N sub 1 with water moving to glass. So we now have an angle of refraction equal to 26.4 degrees. So we're going to change now again. We have air to glass. So we have 19.5 degrees. So N sub 1 is air, then that one is glass N sub 2. So we are now going to use the custom, which is 1.22, air into custom material with index of refraction 1.22. So our angle of refraction is 24.2 degrees. So that's our angle of refraction. So still, you need to determine whether we will come up with the same answer from the simulation and our calculated one. So we are going to use the given uh, index of refraction stated in this video. So let's move on now on our last part before we end our discussion. So we have here, I want you to explain what happened in the picture. So before we end here, so refraction is everywhere because we are able to see through light. So here, there is a chopstick placed on a glass filled with water. And as we notice, uh, the chopstick appears to be broken. So how will you explain this phenomenon? Okay. So this is the virtual laboratory activity for refraction of light. Thank you very much and see you on the next video.